Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some teaching strategies for the math classroom. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our three panelists for tonight: Kyle Atkin, Linda Antonone, and Linda Griffith. For 33 years, Linda Antonone has taught mathematics and science to a diverse population of students at urban schools in both Texas and Ohio. Her passions are helping all students excel and making connections between mathematics and science using technology. Linda, thanks so much for being with us tonight.
Hey, I'm excited to be here, everyone.
And Kyle is currently the mathematics resource teacher for the Kern High School District in Bakersfield, California. He organizes professional development and coordinates the mathematics program for 18 comprehensive high schools and 5 continuation high schools. Prior to that, he spent 13 years in the classroom using TI technology to enhance student learning in algebra and AP statistics, as well as other math courses. Kyle, we're excited to have you here tonight.
It's good to be here, Michael. Thanks.
And Dr. Griffith was a professor of mathematics at the University of Central Arkansas in Conway, previously a co-director of the Arkansas Center for Mathematics and Science Education at UCA. She is currently working as a mathematics consultant for the Wilbur Mills Education Service Cooperative. Dr. Griffith's research interests focus on developing and testing comprehensive programs that result in increases in mathematics achievement. Linda, thanks so much for being with us tonight.
So glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send questions to Kyle or Linda Antonone or Linda Griffith using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. We hope you don't have any audio issues tonight, but in the event that you do, try finding your name in the participant window. In that same window where your name is located, in the lower right-hand corner, there'll be an icon that looks like a phone. If you have audio issues, by clicking that phone icon, you'll automatically begin calling information, and that should resolve any potential audio issues that you have moving forward. This session is being recorded, and as a reminder, we'll provide a link to the event certificate of attendance at the conclusion of the webinar. At this time, Linda Griffith is going to discuss our agenda.
Well, we've been welcoming and making introductions. We're going to move into some discussion about teaching practices and then teacher moves in an activity setting. We're going to look at technology for student-centered learning. And the part I know you are all excited about, there's going to be a chance to win a registration for 2 people to the 2018 2Cubed International Conference, which is going to be in San Antonio this year on March 2nd through 4th. I don't know about you guys, but I'm really excited to attend this event.
Thanks so much, Linda. And Kyle is going to discuss some expected outcomes.
We hope that by the end of this webinar that these will be the outcomes that you'll be able to understand. Talk through some of the teaching practices that are outlined in NCTM's principles to actions. We want to identify some of the strategies that can help support math practices, and especially as they relate to the different kinds of tasks that we do in our daily instruction. And we also want to identify how technology can play a role and how it can support the implementation of those practices that we talk about.
Kyle, thanks so much. It's all yours. Feel free to share your screen.
Thank you very much. We want to talk first about NCTM's teaching practices. We we felt we'd be remiss to have a webinar about teaching strategies and really not bring these mathematics teaching practices that NCTM has come up with in their new publication, Principles to Actions. Probably not new now; it's been a few years. But these are the 8 practices that that NCTM has come up with in terms of mathematics teaching. The incorporation of these can facilitate a good instruction overall mathematics lessons. As we take a look at these very quickly, the first one, establishing mathematics goals to focus learning, really is the way to start on anything. You know, what is it that the math, what is the math that the students really will be doing? What will they be learning during the particular lesson or during the unit? Have we defined that explicitly for ourselves and for students? And is that math appropriate for the students we have, for the grade that they're in, for the skill level that they have? And then also as well, once we've kind of defined what those goals are and been explicit about that, all the decisions that we make in our instruction as we go throughout our instruction in the classroom are based on attaining those particular mathematics goals. So we have to start there and focus on those goals. The second one is about tasks, and I really think that this is extremely important that we have the right tasks that can move the instruction forward. We want tasks that can motivate the learning that kids are going to engage in. Tasks that have multiple entry points, that all levels of skill of students that are in our classes can buy into and get into the task. But we also want tasks that can take the math to the highest levels that you possibly can. I had a colleague once say, we want to be able to milk all the math that we can out of the task, while at the same time keeping the cognitive demand of the task high. And we also want tasks that can encourage multiple approaches, so we can have a varied degree of strategies and approaches to solving those particular tasks. The next one, talking about connecting mathematical representations. Going back to the tasks, we want to select tasks that can encourage this, that we can look for tasks that can help us to connect graphs and tables and equations and graphs and equations and tables and all these, and the visuals that accompany all of those. And we really want to try to select tasks that can do this. We also need to provide times for students to be able to engage and actually try to make those connections and provide time for that. Part of doing that is allowing students to use visuals, to use drawings, to use the technology to help them reason, to help them explain their thinking in terms of making those connections. Facilitate meaningful mathematical discourse. We're going to talk a lot about this a little bit later, especially in the work of John Hattie, but Hattie states that this actually has one of the greatest effect sizes for student learning, an effect size of 0.82, which is extremely good in terms of moving student learning forward. But we're going to talk about, the 5 practices for orchestrating effective discussion, selecting and sequencing the student responses so that the discussion can be meaningful. We really want students to be doing the talking about the mathematics so that they can be the ones putting forth the ideas more so than the teacher being on the stage. Along with that comes posing purposeful questions, and this really has to specifically be thoughtful and thought out ahead of time. We want to make sure that built into our lessons we have questions that push thinking forward, that really tries to extend the thinking of students. We want questions built into our lessons that can probe student thinking to make the math that they're coming up with more visible to us as a teacher, so that we can help to define the directions that we need to go to support those students, and also more visible to the other students around so that they can see the different strategies and solution strategies that other students may have. We also want questions built that can scaffold to support students as they need appropriately, all at the same time making sure that we're not lowering the cognitive demand on the task with the questions that we ask, that we try to keep that cognitive demand at a high level. building procedural fluency from conceptual understanding. You know, trying to get the students to really analyze why does the procedure work? Not just giving them a rote procedure to do, but really studying and trying to figure out why does it work. I have another colleague who doesn't let the students in her class use any procedure that they can't explain why it works, which is an interesting idea. Also, you know, taking the student ideas that they're coming up with, the procedures and the explanations and the reasoning that they're coming up with, and trying to generalize that. So starting with that conceptual understanding, letting the students come up with their ideas and creations, and then trying to generalize that to the procedures that we want them to be able to do. And then making sure that there is some practice with that, but it's meaningful practice that can incorporate the different skills that they've been learning at that particular point in time. Supporting productive struggle obviously is one that is on the bandwagon a lot nowadays. This idea of lesson imaging, I don't know if anybody's heard of this idea of lesson imaging versus lesson planning, where lesson planning really is the idea of kind of pacing out your lesson, structuring it, making sure you know what you're talking about, the goals and things like that. But lesson imaging really plays out to be, how do you envision the lesson actually going with your students? Where do you envision them struggling? When you ask questions, how do you envision them answering? You know, what are the possible responses that they're going to give you, and then what can you do about that response? Which direction are you going to go with it? All at the same time making sure that we're not lowering the cognitive demand, that we're keeping that cognitive demand high. Along with productive struggle, you know, is mindset as well. We want to make sure that the growth mindset, that we're encouraging that growth mindset of students, so that they can have the right frame of mind to be able to tackle mathematics that we want them to grasp with. And then lastly, elicit and use evidence of student thinking. This is the whole formative assessment idea, I think, but really asking ourselves, you know, how will we know that they've met the mathematics goal that we've started out with? What do we have in place within the lesson or within the unit that's allowing us to elicit that student thinking, and how are we going to use that evidence in order to determine if they're on track throughout the entire lesson as well. So as we start tonight, we wanted to kind of set that tone with going through some of those teaching practices that NCTM's brought out. We've really tried to focus on a lot of these as we've developed some of our resources that we've been using. I've highlighted a few of them here that we're going to focus on in the next part of this webinar. We're going to take a look at these particular four and look at those a little bit more closely in terms of an activity setting. So I'm going to go ahead and pass the baton over to Linda and Tanone. It's all yours, Linda.
Thank you. Okay, here we go. So one of the things, you know, when we all got together and we tried to think about how are we going to do all of these, you know, how do we put together something to help people figure out what to do with all of this? One of the things we looked at are lots, trying to come up with tasks, but also looking at some different resources. So we're going to look at this activity, X marks the spot, and Kyle talked a little bit about John Hattie's book, and this is Visible Learning for Mathematics. So this is one of the things that we used, and we're going to be talking about that in this activity. And T-Cubed is actually doing a book study on this, and you can find that at tcubelearns.org and follow along on Twitter, and that's going to be happening this semester. So if you're interested in learning more about this book or reading it and being able to talk about it with some other people, that's a great opportunity to do that with people from all around the country. So basically what this book has is the learning intention's clear. There's a challenging process criteria that's obvious. There's a range of learning strategies that include peer work and discussion. The teacher understands teachers understand and notice when students are not making progress, and they provide feedback. So as students are doing activities or working in classroom, hopefully we know that we're walking around, not just sitting at our desk, give them an activity and let them go over and work, but we're monitoring and looking at what they're doing and listening in on all those conversations. Students say, how did you hear what I said? You know, I can hear what they're saying from across the room and kind of key in on where I need to go based on just kind of listening. And when the students are finished with the task, they want to do another one, which is what we hope. So here's an activity that we put together. I think Linda Griffith actually came up with this. So, and I've got some student work to go along with it as far as how students might approach the problem. So you have two gas wells, and this is like gas drilling is big in lots of parts of the country right now. And there's a pipeline that carries the gas out of the field, and it runs along the south edge of the field. There's a country road that runs along the western edge, and the pipeline and the road are perpendicular. So here's a graphic that shows what's going on, and I'm going to go back. So you have the pipeline at the bottom, you have these two different wells, and on the left side, on the west, you see the county road. And so what you want to do, what the students are going to have to do, is the positions of the wells are given in miles with the intersection of the road and the pipeline as the origin. So that's down where those intersect. Your task is to determine the best point on the pipeline so that the lines from the two wells can both connect to the pipeline at that point. And the goal is to minimize the amount of pipe needed to connect both wells to the pipeline. And they must both connect at the same point because the cost of the connectors is much higher than just the pipe. So what students have, they're given this, okay, and they have to first of all try to understand the problem and figure out, and then they have to basically, here's what we kind of lay out for them. Pose the problem and ask participants to work, or students, independently for about 5 minutes. So lots of times we don't want students to just start talking immediately, because then sometimes one person's idea takes over and the other people haven't even had a chance to think about it yet. So the purpose is to give everybody a chance to process. Next, we want students to collaborate with a partner or maybe a group. My students work in groups of 3 to 4 generally, and so they have to kind of think about it first. Sometimes I ask students just talk to each other first. Sometimes they work in a whole group. This is an activity that we'll have them do in a whole group. So to accomplish the main purpose of the task, you need to think about various approaches students might take. So this is part of planning and anticipating and thinking about what might happen. So one thing you might do is run a wiki stick from the well to the pipeline and have students actually go on a piece of paper and run some wiki sticks and try to like pull it together and so that they can see and visualize with a manipulative. Some students might do guess and check. Okay, so you could say all of these things, you might just say, leave it open-ended. Things are available to you. You have wiki sticks, you have paper, you have rulers, you have different things available, and students can choose what they want. Some students might do guess and check and try several different points along the pipeline, figuring out the distances, make a table, and try to maybe make a spreadsheet and figure out what's going to happen. Another thing is students might try to come up with an equation that calculates the total distance and then minimize that. And so algebra and calculus could be used, and it might not be as simple as just doing guess and check. What's a wiki stick? A wiki stick is like a little, somebody give me a good explanation. So you can look them up. They're like little waxy sticks that you can break or bend. And so students could use those. You could use string. Pardon me?
It's string that's been dipped in wax.
Right. We use them sometimes on unit circles, too, to figure out what a radian is. You know, you make the radius, and then you bend it around the circle to talk about what a radian is. It's pretty cool. And we have kids that make graphs out of them. We do things in calculus with them. They're really a cool thing. If you haven't seen them, you should check it out. This is some sample work that we have. So if you look at this one, they basically looked at the two wells, figured out and said, well, the total distance, D1 plus T2, is going to be how much pipe. and made a sketch. Now, at the bottom, they looked at maybe these two triangles have to be similar. They weren't sure, so they were using that approach. But then on the right-hand side, you notice they looked at, okay, we're going to use the Pythagorean theorem and figure out an equation for D1 and D2 and add those together. And then they made a graph and sketched it out over to the right. And Kyle's going to show you some examples of that in a little bit more. So this is one group. They used two triangles, graphed the sum of the distances to find the minimum. Now, if you look at this as another group, they pretty much did the same thing. However, what do you notice about the explanation and the work that they showed compared to the previous one? Not as much thinking is shown, and one of the things that we really want to stress to students is that we want you to make your thinking visible. We want to see what you're thinking, and the people that are reading your papers want to see what you're thinking, as well as all the students that you're sharing your work with. So when they have to go up and explain, we want to make sure that everybody understands what their thinking is, and this is something that I struggle with my students all the time, helping them to understand why they need to give more of an explanation. So here's another group. So they connected the two wells, and then they dropped straight down to the pipeline. So the question is, does this meet the criteria posed in the problem? Yes or no? What do y'all say in the chat? Any ideas? Do you remember what it was? Yes? Anybody else? I'm looking at the chat. So remember it said that the two had to meet at the pipeline at the same place because the connectors, yeah, I could go back and show you the original problem, but basically it said that the two, the connectors were more expensive, and so what you wanted to do was only have to make one connection so that the two pipelines should both meet on the pipeline at the same place. So if that's true, does it meet the criteria? The answer is no. However, when you look at the distance, some might argue, well, this distance is smaller, so maybe it could become more cost effective. And so, you know, when I'm doing this with kids, I don't want to totally throw it out and say, okay, you know, this is horrible, you're failing the activity, but say, okay, well, let's talk about this. Does it meet the criteria? No. But is there an advantage to this? Yes, it's probably a shorter amount of pipe than was used. So somebody would have to then really analyze, okay, how expensive is the connector versus the pipe, and could this be a viable alternative? And maybe it is. Then you still bring out the fact that maybe they didn't meet the criteria, but also allow them to say, okay, but this might be good depending on what happens. Let's see, what's my next one? Hold on here. Somehow I got into the chat. Okay. Okay, so now what did this group do? So here you see their work. What did they do? I'm checking it out. You guys have ideas? Trial and error, yes. Okay, Colleen says trial and error. And so somebody else is saying, yes, we can learn from things that don't meet the criteria as well. So this one did trial and error. Now you notice what? They did two things, correct? Okay, so they didn't really do very many. And maybe they would need to do more and maybe make a table to show their work a little bit more clearly. But you can see that they're getting closer. So the green one, they did color code at least so that we could see it. So the green one is got definitely more pipe, okay, and the black one has got less pipe, and it looks like it's actually not too far off from what you get when you graph it. And so what's the advantage of just and check? Are there advantages to that? I always tell kids, yes, that's good, but then you want to be able to look at other methods as well. Hold on here. Okay, so one of the other books that we looked at, and I think TCube did it, at least as instructors, we did a book study on this several years ago. That should be practices up there for orchestrating mathematical discussions. And this is an NCTM publication, and basically it says there are 5 things that you want to do with activities. 1, you want to be anticipating what's going on. You want to be monitoring. The selecting and sequencing is kind of important, because if I have an activity like this where I've got several examples of student work, I want to be able to think about how do I have students presenting those. So, and who's going to present? So it could be that several groups did the same thing. So you don't just randomly say, okay, group one, let's go do your presentation. You want to look and select which groups do you want to have present based on what they did, okay? And then you want to sequence those activities so that maybe as you move along, so maybe I would do the guess and check first. Maybe I would do the one that didn't meet the criteria second, okay? And then maybe it's total opposite order of what I showed you, okay? So maybe I would move to the next one where they had the two triangles, didn't show as much work, and then another one that shows, now look how much more detail is here. They have the graph shown, and they can see more so that students kind of get a progression. Or if there are different kinds of approaches, maybe somebody used calculus and somebody used algebra in an advanced class. You might move to the calculus point later, okay? Maybe somebody's using geometry. So you want to select and not just randomly choose groups, and then you want to try to make connections among what all of those students did. So it's really kind of a cool way to do that. All right, I'm going to turn this over to Kyle because he has an extension on this activity that you can use with technology. Maybe Kyle. Okay, Kyle, I think you have it.
Got it. I got it. So we wanted to kind of show a little bit about, how can the technology, support and facilitate an activity like this. So what I have here is just a general setup with the TI-Nspire, just a simple notes page, descriptions of the actual activities, just like we saw, and then a graph page set up with the wells on them and the coordinates placed according to their coordinates, with the county road and the pipeline still perpendicular, meeting at the origin, just like it's described in the problem setup. So with the technology, this might be given to students and sent out to their devices, to where they could, come up with some strategies here to help solve this problem using the technology. Some of those, just to give you an idea, we talked about, as Linda talked about, guess and check. So looking at the solution just based on inspection. So the technology here can allow us some facilitation of that, where we could draw a couple segments from the wells. We could use the software to measure the lengths of those, and then actually kind of drag that connection point along the pipeline here and look at, what is the sum of these two pipelines? What is the length of the two pipelines here? That's up here in the top right-hand corner. So where does that seem to hit kind of a minimum? It seems like I'm getting smaller and smaller and smaller here. So now it seems like I'm getting a little bit bigger. So somewhere around this area, 7739, somewhere around 7.73 miles from the county road along that pipeline would be potentially a connection. So this could be a solution strategy that the technology could help, rather than going through all those guess and checking. We might want students to start out that way, and then we can present them when they're ready with the technology that can say, hey, instead of having to do this over and over, maybe here's the technology that can help you facilitate that line of thinking that they've already come up with. Another solution, excuse me, as Linda mentioned, is based on a graph, defining an equation to represent that total length of the pipe, and then graphing that equation and finding that minimum length. So that's set up here, where we have kind of the same setup, but those are meeting at this particular point, and we're kind of trying to figure out what's that point that can minimize this. So using the distance formula, again, this could be done. It doesn't have to be done in a calculus class. It could be done in a lower level class. It can be done in a middle grades class that's studying this type of concepts. But we can define that function based on just a simple distance formula and define that function that represents that, and then go to a graphs page and look at the graph of this. So I'm going to show real quick, just go to a quick zoom so that we can get that graph, and really kind of look at where's the minimum value here, because that minimum value would give us that x value that will provide that minimum length of those two pipelines. So using this technology to analyze that graph and really find that minimum, that lower bound and that upper bound, and then look at that minimum, we could see here that 7.38 miles from the origin, from the county road along that pipeline, is where we would find the point where we want to anchor that, and the minimum distance of those two pipes together would be 7.74 miles. This is the TI-Nspire software that we're using, that TI has available for the TI-Nspire handhelds. Another one that we saw was the use of proportional reasoning. And with proportional reasoning, this one, there are some assumptions that are made at the very beginning of this, and so having students discuss that certainly would be something that we would probably want to do. But we saw this proportional reasoning where we can define, just how far past that first well along the pipeline do we want. So we can define kind of couple triangles here, and again, this is where the assumptions come in, set up some proportions, and then be able to solve that proportion. So using this on the TI-Nspire, this is the computer algebra system version. So I can tell the calculator, I just want to solve that real quick. Oops, I want to solve that for that variable. And so 2.58 miles from this well is where I would find that value proportionally. So again, just some ways that perhaps the technology can help facilitate some of the learning for this particular task. I'm going to stop sharing that and pass the baton to Linda Griffith to take us on another adventure, another activity.
Okay. So when we started, Kyle was showing us those principles of mathematics teaching, and he talked about selecting tasks. And two of the things said that we needed multiple entry points and we need multiple strategies. So another example that I thought we might take a few minutes to look at is the task that's called the Nardo ring, and I think Dane Ecklert was the first one I saw doing this. It's a 3-act task. There's a video where you see the Nardo ring is a racetrack in Italy that's circular, and the video shows you two cars, a Honda and a BMW, that are going to race around the track, but the Honda gets a head start. And so with basically 4 pieces of information is all the kids get. So this is the first one. It is oops, that's not good. They know that the diameter of the track is 2.5 miles, and they know that the angle, the head start from where the Honda started, where the BMW started, that's 97 degrees, and they know that the speeds of the two cars are 80 and 60 miles per hour. The BMW obviously going faster. So the students take these 4 pieces of information. So there's multiple entry points. So in the class where I field tested this, working with a teacher, these are the kinds of things that kids first came up with. They first came up with the idea that they could find the length of the track, that they could convert miles per hour to miles per second to answer this problem, that the Honda's head start, if it was 97 degrees out of 360, would be about a little over 2 miles. They were able to tell me that the Honda took about 127 seconds to travel the head start, and that how long it would take the Honda to make a lap and how long it would take the BMW to make a lap. So these are the first kinds of results we saw. So there are multiple points you can get started and figure out some things. So to show you the different kinds of representations they used, this is some work from an 8th grade class where they had been studying lines, and the blue line is the Honda, the intercept shows the head start, and then they can see that intersection point happened, but by the time they intersected, the race was over, so they knew that the Honda won the race. Another approach that students took using the TI-84 technology was they made tables. They made a table for the Honda and a table for the BMW, and then they made another table. They looked at the time for the Honda for the head start, and they looked at the difference, and they were able to make a conclusion that, again, that they took a very different approach, a numeric approach. And then I had 2 or 3 groups of students that didn't use either graphs or tables. They simply performed calculations and were able to come up with the different numbers here to see that the Honda did finish before the BMW. So those are all interesting approaches to this problem. So the problem was also posed in my study with a group of pre-cal students, and they took similar approaches, but then we had been studying parametric equations, and so they took on the challenge of trying to animate the race. So they began by setting their window and looking at they imported their background into their TI calculator, which they loved doing that, and then they tried it. They first just put in some simple equations, and they were able to get the picture of the circle, but they said to me, so this is an example of productive struggle. It didn't look like the car's racing. So they went back to the drawing board, and they worked on, we'd been doing some work on changing periods, and so they were able to do some calculations on their calculator screen and come up with some ideas about how to change the period. So then they did that, and they could see both cars going around, but then the Honda, there was no lag between the start for the Honda and the start for the BMW. So then we had to do one of our little tricks that we do on the 84, which was we divided by t greater than 127 to get that lag time to start for the BMW. And at last, they were very, very excited that they got the thing to run. They could see both cars. They could actually see the end of the race. So afterwards, I asked students to just give me some thoughts on their experience with doing this problem. And these were the comments I got. They said, hey, I finally understand this change in period stuff. That was a couple of them said that. And then the guy that made, in the 3-act videos, for those of you who don't know, there's a 3rd video that shows how it actually turned out. So the guy that made the 3-act video must have done sort of what we did. And then one kid said, boy, this class period went fast. And then another one said, do you think, or I bet they use parametric equations in animation. And then one of them said, I'm still not sure about that dividing by t greater than 127 deal, but it worked. And then they wanted to know if they could do another problem like this tomorrow. So I think that's an interesting way for students to think about these different approaches to this problem. So I am going to attempt now to move this over back to Linda to help us finish up tonight. So let me see if I can do this successfully. There you go, Linda.
Okay. So one of the things that, you know, when we were working on this, we came, you know, and this is the struggle that I have as a classroom teacher. I look at it and I say, okay, this is great. This activity was great, but, you know, how do I come up with activities and things to do every day? Because I'm, you know, I'm a regular classroom teacher. Right now I teach 6 classes a day. I have department chair for 21 teachers. I have 146 students, and I'm thinking, how do I, like, just, I can't write my own activities all the time and necessarily look for my own activities. So, you know, it gets me thinking about, like, what do I do in my everyday classroom? How do we find tasks that change our teaching strategies with topics that we teach on a daily basis? And so this is just one example to think about. Think about the introduction to exponential functions, and this is taught now at all different levels. And what are some options for teaching this topic? So in the workshop, we had people share these ideas with their group, but I've tried to move from in my classroom more from instead of saying, okay, here are some exponentials and here's how let's look at 2 to the x. Okay, I changed to explore the characteristics of the exponential function. It has this form. How does the effect of b affect the graph? So, you know, we had a handout for the, I don't use a handout in my classroom, but this is basically what it looks like. Try each of the following values for b and record your findings. Now, it's really cool if you have a navigator because students can try, you know, so for part 1, b is greater than 1. One person tries 2, one person tries 3, one person tries 4.5. People try all different kinds of values, and I can pull up their graphs and we can all look and say, okay, now what happens when b is greater than 1? And then have them look at what happens when b equals 1. So students can go and do this exploration, and I can have them do it on different pages. If you don't have a navigator, you can have students, if you have a document camera, kids can bring their calculators up and show them. They can each take a different value in their group and say, okay, if you're doing values of b where b is greater than 1, make sure that everybody in your group chooses a different value, and then they just lay their calculators down next to each other and compare, and then write about what's happening there. What happens when b equals 1? What happens when b is between 0 and 1? What happens with b is 0? And the other option is what happens when b is less than 0? And so instead of us saying, you know, usually what a lot of people say is when we have an exponential function, here's what we want to do. We want to start out and say, well, you know, you have to have b, when b is between these values, here's what happens to the graph. You have exponential decay if b is between 0 and 1. If b is greater than 1, you have exponential growth. And kids are memorizing these ideas without really understanding. So if we can move students to, in our everyday life, away from this to, I don't have to have a big task all the time, but I do want to turn things over to kids so that they're exploring using technology and they're coming up with their own ideas and putting it together. And you can use most of the activities that we came up with for this workshop, you can use any technology. So while Kyle showed some cool things that you can do on the Nspire, you could basically still graph and find the minimum on an 84 or whatever calculator you have, or kids can use computers. You can do lots of different things. This was, I'm going to show you, do any of you know what happens when b is less than 0? So what happens if I take negative 0.5, raised to the x? And this is one that we don't usually try, so some of you might not know what's going to happen here. Uh-oh.
Parentheses.
Oh, yeah. Thank you. I was like, what happened there? Okay. Thank you, Linda.
You're welcome, Linda. That's why we're a team.
All right. Let's put the negative inside. I thought, uh-oh, that did not go right. Thank you. Okay. Now let's try it. Okay, so what's going on here? And, you know, I talk to kids about this is why, so anybody want to add anything in the chat? Let's see what y'all say. Let me pull up my chat and make sure I have it up. Anybody? What's happening when x is less than 0? So let's think about this. If x is, think about -2. Maybe that would be an easier one to do. If x is -2, or sorry, if the a value is -2, and you raise it to the second power, then it's positive. If you raise it to the third power, it's negative. So it's going back and forth, positive to negative, right? You could ask kids, what do you think is going to happen? So what happens if I make this, hold on, gotta close the chat window, and come back up here and make this, instead of a -0.5, if I make it -2. Okay, so now it's on the other side. Why does that change? And you can talk about why, when we have an exponential function, we want it to actually be a value where we can't be changing from positive to negative all the time and jumping up and down, okay? You can look at what happens when b is 1. Why does it look like that? These are things that are obvious to us, but when kids start exploring them, you find out they're not so obvious to students. And a lot of times I'm finding this out more and more by questioning students as I'm doing a lesson, and I ask them something that I think is totally obvious to me. I did this today. We talked about what's a radian, and we talked about that how the angle has to be, when the radius is equal to the arc length, you have 1 radian. So then I said, okay, now if I have the radius is 2 centimeters and the arc length is 8 centimeters, how many radians is that? And I sent it out as a poll, thinking everybody's going to tell me right away that the answer is 4. And I waited, and I waited. And these are like my top math students. And everybody was just looking at me like, well, what do you mean? You haven't told us how to do it. And I said, but I'm telling you that the angle is 1 radian when S equals R. So now you have to think about what's happening. And it surprises me how many of them just, you know, if they're so used to us telling them what to do all the time that when we say, now you have to think about what all this means, they're really not sure. And it really stresses to me how important it is that we employ these kinds of strategies, that we find good tasks, that we're not lecturing to kids, and that we're making time for them to discuss and come up with conclusions and understand the mathematics rather than the way that a lot of us have done it in the past, or maybe the way that we learned mathematics.
Yeah, and Linda, it's amazing how the technology, what happens in the technology drives those discussions. Like in the example I was showing earlier, they could make the circle, but they couldn't figure out how to make one car go at one time and one go at another. And they really had to talk about it and persevere. But without the technology, we wouldn't have been able to have tried our first. We need the technology to try things, to see what happens when we try it, just like you're doing here in this example.
Right, and I think the other thing that I
just think built into that too is the questioning strategies too. You know, having those questioning strategies and being able to, you know, develop the right questions to ask at the right times, and really planning those out in advance is helpful as well.
And, yeah, Kyle, that goes back to what you were saying about the difference between planning and imaging is, you know, we have to imagine what's going to happen. What's going to happen what are they going to try and what's going to happen, and what questions are we going to ask? And that's a very different approach to planning, other than I'm going to do this problem and this problem. And like you were saying earlier, Linda, we can't have a great task every day, but we can still promote that discourse with some simpler things.
Yeah.
Right, and as a classroom teacher, that's the thing that I kind of try to think about and encourage people in my district, or when I talk to people, is like, how do we do this every day? So we want to have great tasks and we want to do those, but every day I can't necessarily do that, but I can change the way that I'm teaching my class. And the other thing that I do a lot of times, because I'll ask a question and I get blank stares like I see some of you writing in the chat, and so I've started doing, okay, talk to your partner and like brainstorm an idea. And talk to your group of 4 and brainstorm an idea. And then I kind of go from group to group. Group 1, what did you think? What did you all talk about? So then students are less afraid to say something because it's their whole group idea rather than their personal idea. And so plus we get them talking a little bit more and sharing their ideas and coming up with some things rather than us just telling them. And it really does increase their understanding. Plus, it gets them ready for where they're going to move on later in college. And I tell them, you've got to be able to talk about mathematics and talk to each other. But we have to practice those things now and teach them how to do that. And so that's a lot of what all these strategies do.
But that's so different. People are so afraid of being wrong, even when you're in a position like mine where you work with adults. Teachers are the same way. When I pose something to them that's not intuitively obvious or something they haven't seen before, they're terrified of being wrong. But yet, making the mistakes when the learning happens, we need to change the environment of the classroom. And that's part of this teaching strategy is the classroom's got to be a safe place to be wrong.
Exactly. That's exactly right. And when we come back and look at all of these different things and the 5 practices and what John Hattie's book says and the NCTM. I mean, all of these things are talking about a clear learning intention, understanding what students are doing, notice that they're making progress, giving feedback, thinking about how we sequence things in the classroom. And some of that just gets better as we move along and try it. But I noticed some people said earlier, the sequencing part is hard. It is. It's hard for me to kind of try to figure out, and from class to class, kids do different things, and you have to try to figure out how you're going to handle it. And, you know, it's not easy. But this is, you know, what we, you know, this is my 33rd year teaching, and I just keep trying to do things and figure out things and do better every day because,
you know,
I don't have it all down.
In one of my classrooms where I'm working closely with a teacher, we did something. It sounds sort of silly, but it's had a pretty amazing effect. We made a sign. It was a green sign that said, "Today's learning day. You know, making mistakes is encouraged." As opposed to days when we are having to do assessment, we have a red sign that says, you know, summative assessment. Beware of mistakes. So, you know, you just got to do something kind of funny with these kids to really convince them that making mistakes is where the learning happens.
Definitely, and I tell my kids all the time, the research is clear that when you learn more when you make a mistake than when you don't. And one of the things I started doing too, when I'm polling them, and you know, whether you're polling them using whiteboards, the navigator, or whether you're using their cell phones, I'm trying to use polling more and more. And I like to find a question where half the class thinks one thing and half the class thinks something else. And I used to say, okay, now, and I'd give them the answer, but now I stop and I say, oh my gosh, you all disagree. You have 2 minutes to talk to the other people in your group and convince them that you're right. And then I come back and poll them again. And generally, we get to the right answer, although occasionally people convince other people that the wrong answer is right, and we have to go back and talk about it. But it gets them going a lot more than, you know, if I just tell them the answer. So, you know, I'm still trying to figure this out every day, and that's the exciting thing about teaching.
We're learning all the time.
Okay, Michael Houston, I pass the ball back to you.
Thanks so much, Linda. So we're beginning wrapping things up tonight. And if you have any last-minute questions for either of the Lindas or Kyle, please feel free to get those asked. I know they'll do their best in the remaining minutes here to get those questions answered. So we had a couple comments about some resources and where to find some of these really great resources and how long it took some of Linda's students to do some of those activities in their classroom or what level they were. And I hope that now that we're kind of wrapping things up tonight, you're kind of stepping back and realizing some of the bigger ideas, some of the takeaways from tonight. And hopefully that, again, are the connections that you're making with your students, the time you're giving them to think about tasks and important problems. So if you visit our website under activities, if you're a TI-84 user, you can find some great activities in the 84 Activity Central. And if you're an Inspire user, there's Math and Science Inspired. And I believe Kyle posted also a link for the Building Concepts in Mathematics. So these are really great. If you check out the top of my screen where we have, it's broken down to fractions, ratios and proportional relationships, statistics and probability, and expressions and equations. So if I just drill down under fractions, for example, maybe not a good example tonight. Under expressions and equations, take a look at my screen for 10 seconds. So these activities that are written for various grade levels really hit on some of those foundational concepts that we try to teach in mathematics. They're all grouped with student and teacher activities, as well as a TI-Nspire file to go along with them. So these are great things to check out. Again, please feel free to visit our website to learn more. Also on our website, the second thing I want to show tonight under the Professional Development tab, if you move down to Free Online Learning, we had a nice large group that were on site, and this is your first T-Cubed Professional Development webinar, so thanks so much to those of you that are joining us for the first time, and thanks so much to everyone else who have been attending more than one webinar. If you're interested in attending other webinars this spring, you can sign up for webinars on the left-hand side. And we've started posting some of the other webinars that are going to be available, again, free to you. They're usually on Tuesday nights. We have an added bonus. This Thursday night, we're going to be hosting a webinar that specifically deals with writing grants. So please feel free to sign up for any or all of these that you feel you may benefit from, and to share this information with your colleagues as well. We're really excited to be talking about the T-Cubed International Conference. I think earlier Charlene mentioned that Kyle and both Lindas, the three of them, are going to be really digging deeper into some of the information they shared tonight in a 2-hour power session at the T-Cubed International Conference coming to San Antonio, March 2nd through the 4th. And so I don't feel like tonight was rushed by any means, but another hour could have really helped sort of flesh out some of these other ideas. So please feel free to join us at the T-Cubed International Conference, and certainly keep a lookout for the Kyle, Linda session, the power session.
We can't wait to meet you.
No doubt. And Linda Griffith, during our agenda earlier today, mentioned that tonight, to one lucky winner, we're giving away a conference registration for 2 to the T-Cubed International Conference. And tonight's lucky winner is Aminda Wells. So Aminda, congratulations. We hope to see you as well as everyone else at the T-Cubed International Conference. For those of you that are waiting to register, I just got an email today that you can still save 15% by registering really, really soon. So again, feel free to visit our website to learn more.
Can I add one thing to that?
Absolutely.
So just so all of you know, I have not missed the T-Cubed conference since 1991. I have gone every single year since then, and I learn things every year. So it's really if you have never gone, it's one of the best professional developments that I can never go to. And like I said, I never miss it, and there are several teachers in my department now that never want to miss it either, that we go every year. So it's really a great conference if you haven't been there.
Ditto.
Thanks so much. When you leave the webinar, a brief survey will automatically appear in your browser. We really appreciate your feedback, and we hope you share your thoughts in that post-webinar survey. To receive your certificate of attendance, go and click that link in the chat window. Also, this is a link for some of the documents that were used tonight. If you happen to miss either of these links, you'll automatically get a follow-up email regardless in a couple days, and that follow-up email will contain a link to the recording, a link to the certificate, and a link to the documents. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. So thanks so much, Kyle and Linda, for everything you shared tonight. I thought, again, the activities were great, and it was great that you shared some of your students' thoughts and comments. Some of those were really really great to hear. So thanks so much for everything tonight. I really appreciate it.
Thank you. Good time.
Enjoyed it. Thank you.
Thanks, everybody. Have a great evening.
Thanks again, and we hope to see you back online real soon. Have a great night.